little bit of this. We kind of left this at a stage where we were reached a roadblock. We do know the derivative of ETX is ETX. This is one way to show it, not prove it. We're showing it. The proof is beyond the course, but I will show you how it works. Yesterday we had a good idea here to first of all do something like this, wasn't it? I think I remember someone suggesting that. So
that was me.
Yeah, fantastic. And then we kind of stopped. What we could do here is factor out e to the x out of the top line. See that? So we can factor that out. And really then we're looking for the limit. So there's a way we can factor that out. So it's like you're looking really at the limit of just e to the h minus 1 over h.
Why is the limit outside? I mean inside.
You could, but the limit is only applying to the h bits. I could write it the other way, but the limit is only applying to the h bits. So I've just factored out e to the x out of both these.
But why is the limit in the bracket?
Oh, I don't need to have it in the bracket. I'm just putting in, you can write it like this as well. Yeah, e to the x, you put the e to the x here. But really I'm looking at what's the limit as h approaches 0 of this. And this was the same problem we had yesterday, that the limit as it approaches this is undefined, isn't it? Because there's no factor, common factor. You can't get a common factor out of h here. You can't get rid of the h. But we can start to test some values using your calculator, which might help us. Like, get your calculators. So let's put in a small value for e. Let's put in like 0.1 minus all over 0.1, and let's see what answer that gets. So e to the power of 0.1. One point 1.05. Okay. All right. Let's put in an even smaller value. Put in a bunch of zeros. Use the same value down here, 0.00001, and then I've used 4 zeros. You can use more. So if we discuss what a limit is, a limit as h approaches 0 is what it's tending towards. A bit like an asymptote. What's it going towards? So it's going towards 1. So no, it doesn't prove. I'm saying this is one way of showing.
You're missing 2 zeros in that one.
Oh, am I missing 2 zeros? Okay. Yeah. So we could do this same process for what we did yesterday as well with one of these other ones. If we are trying to do from first principles like 2 to the x or 3 to the x, what's happening here? We'll do them. They're going to have this exact same thing. Limit as h approaches 0 of 3 to the x plus h minus 3 to the x all over h. And then we can split that up so we end up with 3 to the x factored out. And what we're really looking for is the limit as h approaches 0 of 3 to the h minus 1 over h. Wouldn't that be the same? It's exactly the same. Instead of e to the x, I have 3 to the x. And for 2 to the x, it would be this. Now, what are we expecting to find when we do the limits of these functions as they approach 0? What do we expect? Put in tiny numbers. What are we expecting? Well, let's try. Let's put in loads of zeros, minus 1 over loads of zeros, small number. Well, do it. It doesn't go to 2. I'm putting in 4 zeros just to get us started. So what's that function? So it's 2 to the x times. Yeah, it's 0.693 for this one. What's this one? You can just change the 2 to a 3.
Hold on. Is 1.0 1.098?
1.098. Okay, all right. That's not quite right, is it? That's not what we were expecting. Or is it?
Or is it?
Remember there was, with the second formula we looked at was the a to the x one. And the derivative of the a to the x one, when you look at it, was...
ax ln a.
Yes, ax ln a. So what is ln 2? Those with the calculators.
ln2 is 0.693.
Very good. And ln 3 would be this.
Sick. It's 1.199.
Yes. And what's ln
I said 1.199.
e?
Log EE. ln E is 1.
Is 1. Yes. So that is a showing. We haven't proved it. We just show that it works in all these cases. The proof is beyond the course. It's very difficult. There is temptation to use something called Hopital's rule here, but you can't actually use it, which is in the course. Hopital's rule is a person. That is in the course. We'll get to that, which deals with limits using derivatives. It's H apostrophe O. It is in. It looks like hospital, which H apostrophe O. Yeah, Hopital's. Le Hopital rule. No, it's Le Hop. I can't remember how to spell it. Anyway, it's French. Okay, so we've kind of shown that it works. Not proved that it works, but it does work. This works if it's not E. Most of the times you're going to be dealing with it's going to be e to the power of something, not 2 to the power of something. Okay, let's look at actually dealing with it now. We're only going to be looking at exponentials today. Let's look at these 3 examples down here. Well, let me look at 3 examples, and you can do some in a second. Let's look at these. So I want to find the gradient function. If my y is 2 to the ex plus e to the minus 3x, what would my derivative or my gradient function look like? Right. What is going to be the derivative of 2 e to the x? It is just 2 e to the x. Very exciting. What's the derivative of e to the negative 3x?
E to the negative 3x.
Times by, yeah. So remember, there is a function within a function here, so we have to use the chain rule. So we'll do, so that'll be e to the negative, and then multiply it by negative 3. I can tidy that up a little bit. That's going to be 2 e to the x. This minus 3 can multiply in front, and we get this. Okay, that's that first one done. Second one, we have now this function, e to the negative x. Okay. There are 2 functions together here, aren't there? Product rule, yes. Here's my 2 functions. So my product rule, I'm going to do the derivative of the first times the second plus this x squared, the first times the derivative of this. What's the derivative of that going to be? E to the negative x times negative 1. Times negative 1, because that's a chain rule again. So that derivative of this function is negative 1. So I can just switch this sign, might be easier than multiplying by negative 1. Alex? Sorry. Yeah, no. You're disrupting the lesson by stealing somebody's sandwich. I know. It is asking for trouble. All right, I agree it's asking for trouble, but all right. No, you can't eat it. Will you just sit down?
I can't see my jaw.
Okay.
Take a different seat.
Yeah.
No.
There's like you can still see other seats in the class.
Yeah.
It's constantly going.
Okay. Next one. What does this look like? You could rearrange it to look like a product, but it's a quotient. I'm going to use quotient rule, which is the bottom, v, by the derivative of the top, which is going to be, can anyone tell me what the derivative is going to be? Of the top?
E to the 2x times.
Yeah, 2 e to the 2x. I'm going to just put that in brackets. Minus, remember with quotient rule, there's a minus here, not a plus. Don't make that mistake. Some people did. E to the 2x, and what's the derivative of this? It's just 1. All over x squared. And depending on the question, we can tidy this up. There is a factor we can pull out. Sometimes it can be useful to factor out e to the 2x, and you get 2x minus 1 here over x squared, if you like. That's a little bit tidier for my liking. E to the 2x and both of the factors out could do that here as well, factor it out. For the moment, we don't have to do that. I'll just show you what it looks like. And that is now how we derive e to the x. All right, time for you to do some. This forms part of your homework. The homework will ask you to do at least 4 parts of these 2 questions.